Alright, so today I'm going to be explaining another important paper with the title Towards Deeper Graph Neural Networks, this KDD paper in 2020. Graph neural networks have shown significant success in the field of graph representation learning. Graph convolutions perform neighborhood aggregation and represent one of the most important graph operations. Nevertheless, one layer of these neighborhood aggregation methods only consider immediate neighbors, and the performance decreases when going deeper to enable larger receptive fields. So we studied this observation systematically and developed new insight towards deeper graph neural networks. First, we provide a systematic analysis on this issue and argue that the key factor compromising the performance significantly is the entanglement of representation, transformation, and propagation in current graph convolution operations. After decoupling these two operations, deeper graph neural networks can be used to learn graph node representations from larger receptive fields. So this is a graph convolution operation. This is your propagation and then transformation, or aggregation and then update. People use different words, but mainly we say aggregation and update. This is TSNE visualization of node representations derived by different number of GCN layers on Cora. And this is the quantitative metric for smoothness. First, we define a similarity metric between the representation of node I and node J with their Euclidean distance, like this. So, based on this similarity, we propose a smoothness metric SMV for node I, which is just the average distance between node I to the other nodes. Hence, it measures the similarity of node I's representation to the entire graph. For instance, a node in periphery or a leaf node usually has a large smoothness metric value. So for the whole graph, you just take the average. But why deeper GNNs fail? We argue that it is the entanglement of transformation and propagation that significantly compromise performance of deep graph neural networks. Our argument originated from the following two intuitions. First, the entanglement of representation, transformation, and propagation makes the number of parameters in transformation intertwined with the receptive fields in propagation. So we decouple the propagation and transformation. Now they are decoupled. Z is just, here we only care about transformation, and we decouple it from propagation. It's just a multi-layer perceptron. And C is the number of classes. So after this transformation, we apply k-step propagation. This is the k-step propagation, A to the k. K-step propagation to derive the output feature matrix. A softmax classifier is applied to compute the classification probabilities. Notably, the separation of transformation and propagation processes is also adapted, but for the sake of reducing complexity. And this is the illustration of the proposed deep adaptive graph neural network. First, we do transformation using multi-layer perceptron, and then k-step propagation. So we have decoupled them completely. Now, smoothness cannot play a big role So we propose deep adaptive graph neural networks. Finally, you can use cross-entropy loss for our labeled examples.